Welcome to tutorial number 20, Drill Software 17. You're doing the Radio and Electronics School's standard amateur radio course, and in this and probably the next couple of tutorials we're going to be talking about single sideband transmission. Before we get into single sideband, I'd really like to go over double sideband again, because the differences really between the two transmission systems is not dissimilar. So it's very important you understand double sideband before we go on to single sideband. And what I've got on screen is the basic principle of creating double sideband. We've got a carrier oscillator on 7 megahertz, and if we were just to transmit that, we would just get an unmodulated radio frequency signal on 7 megahertz. And earlier we saw how we could amplify it and convert that to a Morse code or CW transmitter. However, this time we're going to mix the carrier with audio coming from a microphone. Symbol for a microphone, symbol for an oscillator. So we've got 7 megahertz going into a modulator. We've got the microphone attached to a microphone amplifier, and our voice frequency range 0 to 3 kilohertz is being fed into the modulator as well. So we've got two signals going into the modulator, a 7 megahertz carrier and a 0 to 3 kilohertz voice signal. Now the modulator is just a non-linear amplifier. Probably doesn't do a great deal of amplification, but the modulator is only there for non-linearity. In fact, we could really just use a semiconductor diode for its non-linearity to produce modulation. So the modulator, don't get hung up on these things because there's only amplifiers, oscillators and mixers. They're the three primary components in any radio system, and the modulator is just a mixer. It's a non-linear amplifier. It is just a mixer. If mixers occurred in other parts of the transceiver, they would be called mixers. But because this mixer is being used to mix radio frequencies with audio frequencies, for that reason it's called a modulator. Now, if we say the carrier was F1 and the band of modulating audio frequencies, and the band is 3 kilohertz wide, is F2. So F2 is not one frequency, F2 is a band of frequencies 0 to 3 kilohertz. That's our voice that we put into the microphone, and F1 is the carrier that's coming from the carrier oscillator to the modulator. And of course you do know there would be a stage in there, and that stage would be called a buffer. So when we do put them F1 and F2 into the modulator, we get out of the modulator F1. We get F1 out all by itself. We do get F2 out by itself, but because all these circuits afterwards are radio frequency circuits, audio frequencies are not a real concern for us at the output of the modulator. But we'll get F1 plus F2, and remember F2 is a band of frequencies 3 kilohertz wide, and we'll get F1 minus F2. And we'll also get a whole lot of other crap as well, other mixing products. And that's why we would, in a practical system, put some sort of bandpass filtering here. But they're the ones we want: F1, F1 plus F2, F1 minus F2. So F1 would be 7 megahertz. Because our voice is in kilohertz, 0 to 3 kilohertz, I'm going to put F1 in kilohertz. So F1 would be 7,000 kilohertz. 7 megahertz is 7,000 kilohertz. And of course F2 will just take its highest frequency, 3 kilohertz. So F1 plus F2 would be 7,003 kilohertz. Notice the distance there between the carrier and this mixing product is 3 kilohertz. And F1 minus F2 would be 6,997 kilohertz. So when we put audio and radio frequencies into a mixer, which we call a modulator, a nonlinear device, we get these mixing products, which are the ones we want. The ones we don't want, we use filtering to get rid of. And I've put a graphical representation of a double sideband signal up on screen. This axis here is frequency, and this axis is amplitude. And the 7 kilohertz, 7,000 kilohertz or 7 megahertz is the carrier. That's the carrier there. And the band of frequencies from the carrier up to 3 kilohertz, because of we're modulating with 0 to 3 kilohertz, is 3 kilohertz wide, and that is called the upper sideband. Because if we add 7 megahertz to 0, we get 7 megahertz. If we add 7 megahertz to 3 kilohertz, we get 7,003 kilohertz. So we get produced the upper sideband. So it's all of these voice frequencies converted to radio frequencies in there in the upper sideband. That's all we've done. We haven't done anything else except convert these audio frequencies coming from the microphone to radio frequencies. Later on in the receiver, we're going to have to receive them and convert them back to voice frequencies. We don't need both sidebands. Both sidebands are the same, but in a double sideband system, which this is a double sideband full carrier system. So our carrier is present and our upper sideband is present. The carrier minus 0 to 3 kilohertz gives us the lower sideband. So you should remember that with double sideband, the bandwidth of the signal is equal to twice the highest modulating frequency, which is 3 kilohertz, and it's always going to be 3 kilohertz. So the bandwidth of a double sideband signal is equal to twice the highest modulating voice frequency. In other words, the bandwidth of the whole signal, the lower sideband, the carrier, and the upper sideband is 6 kilohertz. The bandwidth of a single sideband on either side of the carrier is only 3 kilohertz. And since the lower sideband and upper sideband have exactly the same information in them, it makes sense then not to transmit both sidebands. It would be much more power efficient just to transmit one sideband and get rid of our carrier, because the only reason we wanted our carrier is so that we could convert the audio frequencies from the microphone to radio frequencies. We've converted the audio frequencies there to an upper sideband, and we've converted the same audio frequencies to a lower sideband, and now the carrier's done its job. We don't need it anymore. So we could eliminate the carrier at this point, and we could eliminate one of the sidebands and put all of our power just into the sideband. 50% of our power is in the carrier. You don't need to know this. But in double sideband, 50% of our power is in the carrier. And that's wasted because the carrier doesn't provide any information. 25% is left for each of the sidebands. So 25% in each of the sidebands. Wouldn't it make more sense if we put all of the energy, the whole transmitter power, into one of the sidebands? And that would involve eliminating the carrier, and it would involve eliminating one of the sidebands. And if we did that, we would have single sideband. And that's what we're going to be discussing next. I'm just clearing this screen so you can have a bit of a look at it. Remember, if you're running Windows 7 or even some of the earlier Windows, there's a clipping tool that you can run and actually grab the screen. Just draw a rectangle around the area of the screen that you want to grab, and if there's anything you feel that you want to print, you can print them. There we are. I hope you understand that, and if you don't, please play this again. And if you're having, or go back and look at the earlier tutorials on CW transmission, and I also gave an introduction to AM again. And if you have any questions, drop us an email, ron@res.net.au. What I've done now is made a very small change. The only change I've made is I've put a special modulator in called a balanced modulator. You do not have to know how a balanced modulator does what it does, but I will tell you this, it's not a complicated device. A couple of little small RF transformers and about 4 diodes is all you need to build a balanced modulator. What the balanced modulator does for us is it suppresses the carrier. So everything is exactly the same as it was before. We'll still get double sideband, we'll still get an upper sideband, a lower sideband, they'll still be 3 kHz wide each. The whole signal will be 6 kHz wide. But what the balanced modulator does for us, it suppresses the carrier. It doesn't get rid of it completely, but it suppresses it a great deal. It suppresses the carrier. Suppresses this. And so in the output here, we no longer have a carrier. And since 50% of the power that we had before in a double sideband system where we had a full carrier, 50% of the power is in the carrier. That means that power is now available to go into both of these sidebands. So we could increase the power of both sidebands, but that's not what we're about. There is a transmission mode called double sideband suppressed carrier, and this is it. But we don't use it, radio amateurs don't use it, I don't think anyone uses it anymore. So what the balance modulator has done in one stage, and it's quite a simple stage technically, is reduce that carrier. The amount of carrier reduction is about 70 decibels. So the carrier is, for all practical purposes, gone. It's still there, but it's very weak. But we still have a double sideband signal. We're closer to single sideband than we were before because we've eliminated the carrier by using a balanced modulator. We now have to work out a way of eliminating one of these sidebands. If we want to transmit on upper sideband, we need to eliminate the lower sideband and vice versa. So we're part way to a single sideband transmitter. Remember, please, the balanced modulator, it's an exam question, it's a common exam question. The function of the balanced modulator is to suppress the carrier. We'll build up the complete block diagram of an SSB transmitter and it'll all come together for you a bit easier then. And then we'll also be giving you a look, even though you don't have to know it, we'll be giving you a look at a practical block diagram of a single sideband transceiver. What I've done is made another small change to our block diagram. We've still got our balance modulator and our microphone amplifier, our carrier oscillator, and our microphone, which is giving us our voice frequencies 0 to 3 kilohertz. So at the output of the balance modulator, we're going to have not single sideband, we're going to have double sideband and a suppressed carrier. Double sideband suppress carrier. Now, suppose we put a very sharp bandpass filter that only passes 3 kilohertz. This filter is got a bandwidth of 3 kilohertz. Remember, our upper and lower sideband is 3 kilohertz. Before we put the frequencies on, before we worked out that the top of the upper sideband was 3000 kilohertz. Sorry, 7003 kilohertz, not 7000 kilohertz. And the lower frequency was 6997. I'll just abbreviate this. And the center would be 7000 kilohertz. So suppose this filter was, its center frequency was there. This filter, suppose that the center of its bandwidth was in the middle of the lower sideband. If that were the case, then only the lower sideband would traverse through this bandpass filter. If the center of this filter, and by the way, this would be an expensive crystal filter, it has to be a crystal bandpass filter to get this sharpness of bandwidth like that. Suppose this filter were centered there, then in that case only the upper sideband would go through this filter. So by using this bandpass filter or sideband filter, we end up with here, after the filter, we end up with single sideband suppressed carrier, which is the type of sideband that all radio amateurs use. So what we have now is the basis of a single sideband transmitter, because at this point here we've manufactured a single sideband and a suppressed carrier. We've done that by doing two things. We've suppressed the carrier by using a balance modulator, and we've used a very sharp sideband filter to only allow one of the sidebands through, either the upper sideband or the lower sideband. Now I know what you're thinking. This is an expensive filter. A filter like this costs well over $100. What do we do when we want to use upper or lower sideband? Do we unplug this filter and plug another one in? Do we have an upper sideband filter and a lower sideband filter? The lower sideband filter would just let the lower sideband through, and the upper sideband filter would just let the lower sideband through. Well, that would be one way of doing it, but it would be very expensive because we would need two of these sideband filters. An easier way would be to have two carrier oscillators. I'm not going to draw the frequencies up. This is not part of the advanced syllabus, sorry, the standard syllabus. But if we have two carrier oscillators, so we've got two frequencies, we throw a switch and we change the carrier oscillator by 3 kilohertz, we could position the lower sideband to go through the filter using one carrier, and using another carrier only 3 kilohertz away, because the distance between the middle of the lower sideband and the middle of the upper sideband, that distance there is 3 kilohertz. So if we had a switch where we could switch in a different crystal, because the carrier oscillator would be a crystal oscillator, if we had a switch where we could switch in two different crystals, we could position the middle of the lower sideband to go through the sideband filter, or we could position the middle of the upper sideband to go through the sideband filter. That switch is our upper and lower sideband switch, and all it does is shift the carrier oscillator 3 kilohertz in frequency so that either the upper sideband or lower sideband, the one we want, goes through the sideband filter. And that's the basis of single sideband. The rest of this transmitter is going to be just like most other transmitters. I'll point out too that we're going through radio transmission at the moment, and when we come to do receivers, it's really going to be very easy, because it's the same thing, just in reverse from the antenna back to the speaker. So I hope that's clear. I'll do it once more. The balance modulator eliminates the carrier. The sideband filter passes the wanted sideband and stops the unwanted sideband. And by switching the carrier oscillator between two different frequencies, 3 kHz apart, we can either position the upper sideband or the lower sideband to go through this filter. So at the output here, we have single sideband suppressed carrier or just single sideband, either the upper or lower sideband. The bandwidth of a single sideband signal is equal to the maximum voice frequency. So the bandwidth of a single sideband signal is 3 kHz. And that's better because the more narrow band a transmitter is, the more useful its power is, and in the receiver, the more narrow band the receiver is, the less receiver noise we're going to get, and that means we're going to be able to pick up weaker signals. So single sideband is the go for the least amount of noise for long distance communication on HF radio. Now we come to the first practical diagram of a single sideband transmitter. All of this should be starting to become very familiar to you. We've got our carrier oscillator on 7 MHz. The carrier doesn't have to be on 7 MHz. I've just chosen that because it is a low frequency and we want our carrier to be on a low frequency for stability. The lower the frequency that a quartz crystal resonates on, the more stable the crystal's going to be. So we've got our carrier oscillator going into the balance modulator, our microphone picking up our voice signals on 0 to 3 kHz, being amplified by the microphone amplifier, so both of those are going into the balance modulator. At the output of the balance modulator, we're going to have double sideband, we're going to have excuse me, we're going to have double sideband and suppressed carrier at the output of the balance modulator. Then the sideband filter, which is a crystal filter, is going to pass one of the sidebands and block the other one, and that will depend on the frequency that the carrier oscillator is on. It can be switched between two frequencies very close together in order to select the desired sideband. So at this point, we're going to have single sideband. Full description is single sideband suppressed carrier, but we normally just refer to it as single sideband. So we've got the signal we want to transmit at that point. What we haven't got is enough power, and we're not on the frequency yet that we want to transmit on. So let's build up the power with an intermediate amplifier. It's called intermediate because it's not the final amplifier. It's halfway to the final amplifier. So let's build up our signal with an intermediate frequency amplifier, and that amplifier would be on 7 MHz, and it would have a band pass in it. So the IF amplifier doesn't do anything. It's a linear amplifier. Everything after modulation has to be linear, so because we don't want mixing to go on unless we want it to go on. If we had a non-linear amplifier there, our sideband would mix with itself to produce all sorts of rubbish, so that that IF amplifier is a linear amplifier, and it would have a lot of gain. So at the output of that amplifier, we've just got the same thing as we had at the input, it's just bigger. Now we're going to move either the upper sideband or lower sideband, depending on which one we've selected with the carrier oscillator. We're now going to move it to where we want to transmit, and I've just chosen 14 to 14.5 MHz. We're going to need a VFO, and a VFO it's a variable frequency oscillator, and this VFO can go 500 kHz from 7 to 7.5 MHz. When the VFO is on 7 MHz, we'll have 7 MHz going in, and we'll have either an upper or lower sideband on 7 MHz going into the mixer as well, and at the output of the mixer we'll have F1 minus F2, F1 plus F2 I should say. We'll have some other frequencies there as well, but there's a filter in there that gets rid of them, and that would put us on 14 MHz. So if the VFO was on 7, the upper sideband or lower sidebands on 7, goes into the mixer. F1 plus F2 gives us an output here on 14 megahertz. If the VFO is on 7.5 megahertz, then 7 plus 7.5 would put us on 14.5 megahertz. So the VFO, by adjusting the VFO, we can go between 14 and 14.5 megahertz. This diagram, this block diagram, is the one that you need to know for your assessment for single sideband transmission and reception. Recall that a mixer is just a nonlinear device. The balance modulator is a mixer, special mixer which suppresses the sideband, and we've got a second mixer in this transceiver as well. And that is to frequency convert our sideband to our transmit frequency. Just to remind you, the combined name of a mixer and oscillator when we're doing a frequency conversion like that is called a frequency converter. There's our block diagram of a single sideband transmitter again, and I've just removed the carrier and one of the sidebands. I've presumed that we're transmitting on lower sideband. So if we were to look at a spectrum analyzer, this is amplitude. Oop, I've got the wrong pen color. This is a spectrum analyzer, that is amplitude, and this is time. Sorry, frequency. That's frequency, and that's amplitude on a spectrum analyzer. On an oscilloscope, this is what a fully modulated, 100% modulated single sideband signal looks like. You don't need to know the axes of an of a spectrum analyzer, but you do need to know the axes of an oscilloscope. The y-axis, the vertical axis on the oscilloscope, is the amplitude of the signal, and that's the y-axis, and the horizontal axis, this axis here, is the x-axis, and that's time. And what you're seeing on that oscilloscope at the moment is a 100% modulated single sideband signal. If a single sideband signal is over-modulated, the smooth tops tend to get flattened like that. That's over-modulation. And if you do over-modulate like that and you get flat topping on the signal, that will cause splatter. Splatter is really another name for mixing, and that will cause interference to other stations if you over-modulate like that. I hope you're fairly comfortable with the single sideband transmitter. Carrier oscillator goes into the balance modulator along with the signal from the microphone to produce here double sideband suppressed carrier. The sideband crystal filter passes only one sideband, so at this point we have single sideband. We amplify it a lot. At this point we have single sideband. We then change the frequency from 7 megahertz to 14 to 14.5 megahertz using a mixer and a VFO, and then we then go into the power amplifier to give us the power we want to transmit. So we might want to transmit 100 watts. There may only be 1 watt going into the power amplifier. The power amplifier stage is the stage which draws the maximum amount of current from our power supply. Of your 20 amps, if you've got a 20 amp transmitter, of the 20 amps that's going into your transmitter, 18 of those amps to run the power amplifier, because the power amplifier brings the power level after the mixer up to full power with just a couple of amplifiers. There we have it, single sideband transmission. I might just mention one other thing about the power amp. I'll be back in a sec. I'm just going to clear the screen. I just want to mention briefly the coupling of the antenna to the power amplifier. All power amplifiers have a coupling circuit in their output. It's usually not enough unless we've got an antenna which is close to 50 ohms, which is the nominal internal impedance of a power amplifier. So the little tuner in the power amplifier doesn't have a great deal of range. If we were to tune the power amplifier, we have a meter on our radio, and that meter can normally measure output power, or it can measure plate current or collector current or drain current, depending on the type of device we're using in the amplifier. But if that were to be adjusted, it's the same controls that I've drawn here: tune, band and load. Sometimes they're known by slightly different names. But we would simply adjust each one of these controls, two variable capacitors and a variable resistor. We would adjust them alternately for a dip in the output current. A dip in the output current indicates resonance. So each of the controls on your ATU, it could be an external ATU, it could be inserted in there. So it's an antenna tuning unit, ATU. And if we do have an ATU, the easiest way is to monitor the output power and to simply adjust the three controls, tune, load and band, on the ATU for maximum power. And of course you'd give your call sign while you're doing that adjustment on air. Maximum power. There is another way, and you need to know both. You can adjust these three controls for minimum output current, whether it be anode or collector current. If you adjust them for minimum current on the meter on your transceiver, then you'll know that you've got an impedance match here with the antenna tuner. But what most amateurs do these days is simply look at their output power, adjust it up a bit and give their call sign, and then alternatively adjust the three controls, 1, 2, 3, go round them again until you get maximum power, and it doesn't really take long. That's how the ATU works, and that's about all you need to know about ATUs at this stage anyway. I will tell you that the ATU is a low-pass filter. That is a schematic diagram of a low-pass filter, because one of the things that an ATU does is prevent the radiation of harmonics. So if our transmit frequency is 7 megahertz, that will pass through the ATU quite easily, but our second harmonic on 14 megahertz will have a lot of difficulty getting through the ATU. So the ATU is a harmonic suppression device for us. This single sideband transmitter only uses one conversion to get the sideband from the carrier frequency to the final transmit frequency. So we're using this frequency converter here to move the single sideband signal from 7 megahertz to 14.5. That is a single conversion. We could, if we wanted to, we don't have to move in one step like we have done here to 14.45 megahertz. We could, after the mixer, we could have had another IF amplifier, another IF amp, and done some more IF amplification, and then we could have had a second mixer and its oscillator, of course, and then we could go into our power amplifier. So that could go in there. What I'm saying is there's no need to go straight from 7 megahertz to 14.5. In fact, there's a lot of good technical reasons for not doing big frequency changes like that. For stability, it might be better if we started out at 2 or 3 megahertz and then moved to a 7 megahertz IF. We could then move to a 14 megahertz IF, and then finally the power amplifier, and transmit on whatever frequency band we want to transmit on. Even though you don't need to know the full block diagram of a transceiver, particularly for this course, I'm going to show you one in the next tutorial. You don't have to know it, but it will help consolidate transmitters because it's a transceiver. It's got transmission and reception on it, and it's a practical transceiver, and it will help consolidate. Nothing new, just consolidation on what we've done so far. So I'll see you back in the next tutorial and we'll have a look at that SSB transceiver. We won't be looking at the receiver side just yet. We'll just be looking at the transmit side, and I hope that'll consolidate things a little bit for you. Cheers for now. See you back in the next tutorial. This is Ron, VK2DQ.